It's my pleasure to now start the next round of the program, which is going to be, again, we are, as you have noticed today, we have started to dig deep in the technicalities after the very nice presentations by Rainer, Jan, and Marco. Now we are moving towards more on now wettability and thermodynamics of hydrogen. The first speaker, I have the pleasure and honor to introduce her to you all. You have heard a lot from her, from all the emails that you have sent to her. She was checking about 2,500 emails just last week, maybe. All the travel arrangements and all the questions you had. So Maartje Boon is here with us. Dr. Maartje Boon holds MSc degree, Master of Science in Hydrogeology from Utrecht University here in the Netherlands. Suzanne comes from the same university. Welcome, Suzanne. And obtained her PhD in petroleum engineering from Imperial College London, where she worked on reactive transport with applications for geological carbon sequestration. She did a postdoc at Stanford University ERE department. There are many colleagues from ERE departments. Mark is here with us. Tony is here. I also did my postdoc at ERE as well. Sam was here. He did also his postdoc at ERE of Stanford. And she focused in her postdoc period of 3 years on the impact of rock structure heterogeneity on multiphase flow properties and its implications for geological carbon sequestration. For her work, she combines numerical and analytical models with experimental observation to describe processes, complex processes in porous media. Maartje, we are all looking forward to hearing your lecture.
Okay. Well, thank you very much, Hadi, for this nice introduction, and thank you for giving me the opportunity to give this lecture today. We all know that we can store hydrogen underground in salt caverns, but also in porous reservoirs. And this talk will be focused on underground hydrogen storage in porous reservoirs. So here you see, on the right, you see a porous structure, and these channels are initially filled with water, and then hydrogen is injected, as you can see here from the bottom, and then the hydrogen is displacing this water. And this sort of mimics what happens when you inject hydrogen into the subsurface. So if we want to investigate the feasibility of underground hydrogen storage, we need to know how this hydrogen flows through this porous structure. And that highly depends on the wettability. So the wettability is the tendency of a fluid to spread on a solid surface surrounded by another fluid. So if you would have, if your reservoir would be hydrogen wet, then the hydrogen would spread or cover the rock grains. And when you would inject the hydrogen into this reservoir, then the hydrogen would spread even or flow even through the smallest pores, as you can see right here. However, if your reservoir would be water wet, then water would be covering the rock grains. And if you would inject hydrogen into this water wet reservoir, then the hydrogen would be mainly flowing through the biggest pores, as you can see right here. So now this wettability also has a big impact on what happens when you want to reproduce this hydrogen again. So in the case of a hydrogen wet system, when you want to extract the hydrogen out of this reservoir, then the water will be displacing this hydrogen, but now the water will be flowing through the biggest pores, and a lot of your hydrogen will get trapped. However, in this water-wet system, the water will be flowing even through the smallest pores, and you will be able to get a lot of your hydrogen out, so you will have less trapping. So water-wet systems are favorable for underground hydrogen storage. So I want to make one comment here is that these images are not completely what really happens during underground hydrogen storage, because you, of course, also have cushion gas. However, in a water-wet system, your water will still be covering the rock grains, so even then your hydrogen will be in contact with the water or with the brine. The wettability can be characterized with the contact angle. So it's the angle between the gas-water interface and the water-solid interface, as you can see right here. And this can be determined by the interfacial tension of the solid-gas interface, the water-gas interface, and the solid-water interface with Young's equation, as you can see here. So if your contact angle is less than 90 degrees, your system is water wet and the surface has more affinity for water than for gas. But if your if your contact angle is bigger than 90 degrees, your system is gas wet and the surface has more affinity for gas than for water. So now because of this interfacial tension of the gas-water interface, you have a pressure discontinuity. So the pressure in your water phase will be different than the pressure in your gas phase. And the difference in that pressure between those pressures is the capillary pressure. So in my presentation today, the contact angle, the interfacial tension, and the capillary pressure will be important. So here I'm showing a cylindrical tube filled with gas on the left side and water on the right side. And in the middle you see the interface. And so the interface between the water gas and the water solid, or the angle that you have between the interface of the water gas and the solid water interface is the contact angle. And if the system is in equilibrium, then this contact angle is the intrinsic contact angle. However, if you have a dynamic system, so if the system is moving, then if the water will be displacing the gas, you will have an advancing contact angle, and this is what happens during imbibition. When you're reproducing your hydrogen, you will have advancing contact angles. And if the flow is from left to right, so the gas will be displacing the water, then you have receding contact angles, and this is what happens during drainage when you're injecting your hydrogen into the reservoir. So now, as I said in the previous slide, there is a pressure difference between the gas phase and the water phase, and this pressure difference is the capillary pressure. And for a circular tube like this capillary pressure can be calculated with this equation right here. And you can see that this capillary pressure is dependent on the interfacial tension between of the water-gas interface as well as the contact angle and R is the radius of the tube. So if we look at a porous medium, then you can look at the space that you have between the rock grains as a circular tube. So then you can see that you can calculate this capillary pressure for each of those spaces, and you can see that now R is actually the pore radius or the size of your pore. So you can see that for bigger pores, you will have smaller capillary pressures, and for smaller pores, you will have higher capillary pressures. So if you want to inject the hydrogen into this porous reservoir and you want a flow to occur, you have to overcome this equilibrium capillary pressure. And so if you increase the pressure in your gas phase, then you will start to enter those pores, but you will first enter the biggest pores. So flow will first happen through the biggest pores. So if you look at this as this box that you see here on the left, if you look at that as a porous medium, and the inlet of this rock will look like this, what you see here in the center. So the blue are pores filled with water, and the gray is the rock structure. So if you now want to inject hydrogen into this rock, then hydrogen will first start to enter the biggest pores because they have the lowest capillary entry pressure. And then when you start to increase the pressure in your hydrogen phase, you slowly start to invade smaller and smaller pores. And in this way, you can construct a capillary pressure curve, as you can see right here. So now you can see from this equation of the capillary pressure that the capillary pressure depends on the interfacial tension and also on the contact angle. So if we would lower the interfacial tension, also this capillary pressure curve will change. So you will shift your capillary pressure curve down, which means that for the same capillary pressure, you will now have higher wetting or gas saturations. So now if we look at the contact angle, so if we would increase the contact angle, so if we would make our system less wetting, we also shift down this capillary pressure curve. And again, for the same capillary pressure, you will have higher gas saturations. So now these saturation distributions also have a big impact on how easy it is for the hydrogen to flow together with the water through this porous system. And that can be characterized with the relative permeability. So here on the right you see a relative permeability curve. So on the y-axis it's relative permeability, and on the x-axis you see water saturation. And this is the curve for the water phase, and these are the curves for the non-wetting phase, and in our case, hydrogen. So if your water saturation is very high, your relative permeability in your water phase is very high, and then if you start to get more gas in your system, the relative permeability of your water phase decreases, and the relative permeability of your hydrogen phase increases. So the black line here shows a curve for a very strongly wetted system, and the dashed line shows a curve for when the system is more weakly wetting. So you can see that these curves then shift to the left. So also your relative permeability is highly dependent on the wettability. So during underground hydrogen storage, you inject and extract hydrogen in multiple cycles, and your relative permeability will not be the same. So you have a different relative permeability and capillary pressure during injection, during drainage, and you'll have a different relative permeability and capillary pressure during imbibition. But then when you have your next cycle, your drainage and imbibition curves also change again, because during each cycle you can get more and more of the hydrogen trapped into your reservoir. So these curves, they change. So to investigate the feasibility of underground hydrogen storage, we can use reservoir simulators, and important input parameters for these reservoir simulators are relative permeability and capillary pressure. So now if we want to correctly model what is happening in the reservoir, we need to use relative permeability and capillary pressure curves that accurately capture the characteristics of the hydrogen brine rock system. So we need to accurately characterize these curves. So to derive meaningful relative permeability and capillary pressure curves for the hydrogen brine rock system, we can characterize the wettability and then use these contact angles and interfacial tensions in pore network modeling, and then derive these meaningful rel perm and capillary pressure functions. Another way to derive meaningful rel perm and capillary pressure functions for this system is to directly measure those parameters in the laboratory. And from these experiments, you can also characterize the wettability. Here I'm showing a graph of natural gas underground storage fields in the United States, and you can see that there are plenty of them, and they've been storing natural gas underground for many, many years. So why do we think that underground hydrogen storage would be so different than, for example, storing methane underground? So the reason is that they have very different properties. So here you can see the density, the interfacial tension, and the viscosity for hydrogen and methane. So you can see that the density is much lower for hydrogen. You can also see that the interfacial tension is much lower for hydrogen, and also the viscosity is much lower for hydrogen. So as a result, you can expect that there will be a very complex interplay of viscous, capillary, and gravitational forces, which can lead to very different flow behavior than what we have observed for CO2 or other gases. So now I'm going to show some work that has been done in the last couple of years for the hydrogen brine rock system. So the work of Jekta et al., they carried out, or they measured for the first time relative permeability and capillary pressure for the hydrogen brine system. And they did that for 2 different conditions. So they did it for conditions that represent a shallow reservoir and for conditions that represent a deep reservoir. So you can see those results right here. So on the left, you see the capillary pressure curve, and on the right, you see the Relperm curve for those 2 different experiments, and you can see that there's hardly any difference. So they didn't really observe any pressure or temperature dependency right here. So from these capillary pressure measurements, they could also determine indirectly the contact angle by combining this with MICP measurements. And they derived a receding contact angle of 21.6 degrees and 34.9 degrees. So this points towards a water-wet system, which is favorable for underground hydrogen storage. So that was good news. However, we still don't really know what is really happening inside the core, because there's no visualization of flow. So after this study, a lot of people have done further or more experiments to directly visualize what happens when hydrogen comes into contact with rock and brine. So several methods have been used to characterize the wettability. So people have used the tilted plate technique, the captive bubble cell approach, microfluidics, and they've measured contact angle directly in real sandstone rock cores. And of course, those measurements that are done inside real sandstone rock cores are most representative for real sandstone reservoirs. However, these other more simple methods can give important insights on the wettability characteristics for underground hydrogen storage. They can, for example, help us to answer the following question. So, is wettability of hydrogen different compared to other gases? Does wettability depend on pressure, temperature, or salinity? And what is the impact of the different driving forces? So let's first look at the tilted plate technique. So during the tilted plate technique, you have a cell that is filled with hydrogen, and you have a tilted plate. And in this study, they used a tilted quartz plate, and they placed a water droplet on top of this tilted plate, and from that they could measure the advancing and receding contact angle. So the main acting forces in this system are gravitational and capillary forces. So here you can see the results of this study. So on the y-axis you see contact angle, and on the x-axis you see pressure. And in red you see the results for hydrogen, and in green you see the results for CO2. And the experiments were carried out for different temperatures. And the dashed line are the receding on the contact angle, and the solid lines are the advancing contact angle. So what you can see here is that the dynamic contact angle increases with pressure and temperature, with contact angles ranging between 0 and 48.3 degrees. So this again points towards a water-wet system, which is favorable for underground hydrogen storage. And also what you can see here is that the dynamic contact angle of CO2 is higher than that of hydrogen. So there's a difference in contact angle for the 2 different gases. So now if we look at the next system, it's the captive bubble cell technique. So in this technique, you use a cell that is filled with brine. So it's different than the previous technique where we had a cell filled with hydrogen. Now the cell is filled completely with brine. And from the bottom of this cell, we release bubbles of gas. So you can release bubbles of hydrogen, and then the bubble rises until it reaches the rock surface, and then it slowly dissolves into the brine. So the main acting forces in this system are buoyancy and capillary. So here you can see the results that were obtained using this system. So if we're first looking at the 2 graphs at the top, so there is contact angle on the y-axis and pressure on the x-axis. And the blue shows the results for pure hydrogen, and the green shows the results for pure methane. And the colors in between are the results for different hydrogen-methane mixtures. And the graph on the left is for 30 degrees C, and the graph on the right is for 50 degrees C. So what you can see here is that similar wettability behavior is observed for hydrogen, methane, and their mixtures. Now, if we look at the graph at the bottom left, There you have contact angle on the y-axis and volume on the x-axis. And there you can see that the contact angle increases with decreasing volume. And you can see that we obtained the exact same results for hydrogen, methane, and their mixtures. So this contact angle depends on the size of the bubble. So from these results, we saw that the static contact angle is independent of pressure, temperature, and salinity, and it ranged between 25 and 45 degrees. And here on the bottom right, you see a result from another study where very similar results were obtained. So again, we can see that this hydrogen water system is water wet. So that was a bit surprising because with the tilted plate technique that we saw, that I presented first, there was this very strong pressure and temperature dependency. And now we do this different technique, and you saw different contact angles for the different gases. And now with this other technique, you see that there is no pressure and temperature dependency, and you also see that all the gases are behaving the same. So we did a theoretical analysis to get a better understanding of what is happening and why we are obtaining these results. So to calculate the contact angle, we fit this equation right here to each contour of the bubbles. And in this equation, there are 3 parameters that impact the contact angle. So that's B, which is the radius at the apex. It's delta rho, which is the difference in density between the brine and the hydrogen, and sigma, which is the interfacial tension. So now if you write this equation in dimensionless form, you can see that the combined impact of these parameters can be characterized with the bond number. And the bond number is the ratio of gravitational forces and interfacial forces. So now we could calculate the bond number for our pure hydrogen and pure methane experiments. And we've plotted that bond number as well as the contact angle as a function of apex radius, as you can see right here. And you can see from this that for under similar bond numbers and similar bubble sizes, the contact angle of hydrogen and methane are comparable. Now, these experiments were carried out for temperatures ranging between 20 degrees C and 50 degrees C, and pressures ranging between 20 bars and 100 bars. However, in the literature, there's a lot more data available for interfacial tension and density for both hydrogen and methane. And we can use these data to calculate bond numbers for a much wider range of pressures and temperatures for both hydrogen and methane. And they are plotted in this graph right here. So what you can see here is that the bond number stays relatively constant with pressure for both hydrogen and methane, and there's only a small change in bond number with temperature for those two gases. So this shows that in real field processes in which buoyancy and capillary are the main acting forces, hydrogen and methane will have similar wettability characteristics. So now we have a question. So if we would study hydrogen-nitrogen mixtures, what would you expect? Hydrogen and nitrogen are very different, or hydrogen and nitrogen will behave similar in this captive bubble cell approach? So who thinks A? And who thinks B? I guess everybody. Well, that's correct. That's correct. So we also did experiments for nitrogen, and we obtained the same results. So all these gases are behaving very similar, or actually the same in this system where buoyancy and gravity, or buoyancy and capillary are the main acting forces. So the last technique that was used to characterize the wettability, or actually not the last, but the simple technique that was used to characterize wettability for the hydrogen brine rock system or glass system is microfluidics. In this system, the main acting forces are viscous and capillary forces. And two studies used this technique. So in one of those studies, a chip was used where there were channels of different widths, and the other used a microfluidic chip that represents a realistic sandstone pore structure, pore structure. So here you can see the results. So for the graph at the top, you have contact angle on the y-axis and capillary number on the x-axis. And the graph at the bottom, you have contact angle on the y-axis and channel width on the x-axis. And there the experiments were carried out for 3 different gases, for hydrogen, CO2, and nitrogen. So what we can see from this is that the dynamic contact angle increases with decreasing channel width between 6 and 39 degrees. So again, water-wet conditions. We also can see that there are similar contact angles for hydrogen, nitrogen, and CO2. And from the graph at the top, you can see that the dynamic contact angle stays relatively constant with capillary number. Only for the very high velocities there was an increase in the contact angle. So now the last method that has been used to characterize the wettability for the hydrogen brine rock system, which is micro-CT. So people have carried out core flood tests in real sandstone rock cores, and they measured the contact angle or contact angles inside this real porous structure and visualized that with the micro-CT. And of course, in a real sandstone pore rock structure, the pores are very different. You have very different pore sizes and also other variations, so you don't really measure one contact angle, but you get a distribution in contact angles, as you can see here in this graph on the right. So the main observation here is that the mean of the macroscopic and apparent contact angle distributions were 39.77 and 59.75. So these are a bit higher than what we obtained with the more simplified systems. So if we summarize all the wettability observations that were made in the past years, you can see that in this graph. It's not completely complete, but these are the most of the results that are out there. So on the y-axis, you have contact angle, and the bars are different dynamic contact angles, or represent the dynamic contact angles, and then the dashed lines are the static contact angles that are measured. So you have first the microfluidic results. The TPM is the tilted plate method. CF stands for core flooding. And then we have the study from Higgs was with in the realistic pore structure, and the CBC is the captive bubble cell approach. So, okay. Yeah, so we can see that the hydrogen brine rock system is water wet, which is favorable for underground hydrogen storage. We can also see that the contact angles that are measured in real cores are higher than the contact angles that were measured using simplified systems. However, these more simplified systems can give us important insights of the wettability characteristics and maybe flow behavior that we will observe for the hydrogen brine rock system. For example, we saw that using the captive bubble cell method, that there was no pressure temperature dependency, and hydrogen and methane behaved similarly. While for the tilted plate technique, we saw this clear pressure and temperature dependency, and hydrogen and CO2 behaved differently. So how will these observations impact the displacement during drainage and imbibition? So recently, very recently, because I found this on arXiv last weekend, people carried out this research where they visualized the hydrogen displacement and trapping in the sandstone rock core at the pore scale. And they carried out these experiments at different pressures. So here you see the results at the top for drainage. And on the pressure, so the pressure increases from left to right. So if you now look at the saturation that they obtained at the end of drainage, the hydrogen saturation, you can see that this saturation is around 50% for all pressures. So again, here was no pressure dependency observed. However, if we now look at imbibition, which they also carried out, you can see a different behavior. Because for an increase for the highest pressure, you can see that the hydrogen saturation is much higher. So a lot more hydrogen gets trapped at higher pressures. So we have this pressure dependency during imbibition, while we didn't see that during drainage. So from these results, we can also see that maybe shallower reservoirs are more favorable for underground hydrogen storage because, of course, we don't want this hydrogen to get trapped. And there's a clear dependency here on the trapping and the pressure. So they also carried out experiments for both hydrogen and for nitrogen. And so here you can see the results. So at the top you have drainage, and on the left here you see the results for hydrogen, and on the right for nitrogen. And again, during drainage there's no difference between the two gases, but if we look at imbibition, you can see that a lot more nitrogen gets trapped compared to hydrogen. So we see that for drainage, hydrogen and nitrogen behave the same. For imbibition, hydrogen and nitrogen behave differently. So this is very similar to what we observed during our very simple techniques to characterize the wettability. When we had a cell filled with brine and we inject gas bubbles from the bottom, we didn't see any pressure dependency and the gases were behaving the same. And that looks very similar to what happens during drainage when you have your core filled with brine and you start to inject the nitrogen. And then when we look at the imbibition, you have your core filled with a lot of hydrogen. And that is very similar to this tilted plate technique where you had your cell filled with hydrogen and you only placed a bubble of water there. So another research that's recently been done, they measured relative permeability for hydrogen water systems. And they also carried out these experiments for a range of pressures, and here you can see the results. So in black you see the results for the lowest pressure, in blue for 10 megapascals, and in red for 20 megapascals. So you can see here that there is a clear pressure dependency here. So here it's relative permeability on the y-axis, but now it's not water saturation on the x-axis, but now it's the gas saturation on the x-axis. So you can see that for higher gas saturations, your relative permeability at high pressure is lower than for lower pressures. And that can be explained by the fact that when you have an increase in pressure, you increase your viscosity, and which lowers the relative permeability. However, for much lower gas saturations, they saw the opposite effect, and that was explained by the fact that when you have an increase in pressure, you decrease your interfacial tension, which then increases the relative permeability. So this is how they could explain their observations. So now we have and from this, again, we see that shallower reservoirs will be more favorable for underground hydrogen storage because there you will have a higher relative permeability. So now we have our second question. So the second question is, in this same study, they also carried out drainage relative permeability measurements for the hydrogen water, nitrogen water, and methane water systems. So what would you expect? Would you expect that the relative permeability of hydrogen is higher than nitrogen and higher than methane? Or do you think that nitrogen will be higher than hydrogen and hydrogen will be higher than methane? Or is methane will have the highest rel perm and then nitrogen and then hydrogen? So who goes for A? Who thinks it will be B? And who thinks it will be C? So why do you think it will be C?
Just a gamble.
Oh, okay. Well, let's see what the answer is. So I think it was indeed C. So it's a pity you're not able to explain it because it is the right answer. And I was actually surprised that this was the answer, or this was the result, because I actually expected that hydrogen would have the highest rel perm here, because I understood the explanation of this previous graph, why at higher pressures it was lower because the increase in viscosity. Then I thought, oh, the viscosity of methane is higher than hydrogen, so they will be swapped around, but it wasn't. So it looks like this. So the question is, why is the relative permeability of methane higher than that of hydrogen? And I think these are difficult questions to answer. And I think the only way to answer these questions is when you really look inside the core and when you really observe what is happening. And I think that is really what needs to be done to get a better understanding of the behavior of hydrogen water sandstone systems during displacements. So we recently carried out experiments where we visualized the flow of hydrogen through a rock core. So we carried out experiments for a Berea sandstone rock core and the hydrogen water system at 100 bar and 20 degrees C. And here you see the porosity map of this core. So it was a bit of an interesting core because we thought it would be an homogeneous core, but actually we had two very low permeability bands inside this core. And that had a big impact on the flow. So we carried out experiments for drainage and for imbibition. So here at the top you see the results for drainage, or not the results, just some images of the results that are interesting, I think, during drainage. So what you can see when you look at the first picture, you can see that immediately before it entered the core, we had this very big gravity segregation where hydrogen was mainly flowing at the top. Then once the hydrogen reached this low porosity zone, which acted as a capillary barrier, the hydrogen was forced to move down. And because of that barrier, a lot of spreading happened throughout the rest of the core. So it was better spread out. So that was interesting. Then we did the imbibition, and the imbibition first started out as normal. And then for this 50-50% fractional flow, we saw suddenly that these fingers started to form, which is also not what you expect, because you would expect that maybe during drainage and not necessarily during imbibition. But it happens anyways. And then, but the system was still behaving sort of normal, because we would reach the steady state quite easily. And then we went to a higher fractional flow, and suddenly we couldn't reach a steady state anymore, or we could reach a steady state, but it would take 4 or 5 hours to reach that steady state. And during that process, these fingers turned into a channel. And we only started to reach a steady state again once this channel reached the outlet of the core. Now, if you want to make meaningful relative permeability and capillary pressure measurements, your hydrogen and your water need to flow through the same pore space. And when you have this gravity segregation that you see right here at your inlet, that is not really happening. And when you have a channel forming, that's also not really happening. So you cannot really make meaningful measurements when it looks like this. However, we were lucky because we had pressure taps at several locations along the core. So we were still able to make those measurements because we could take the section of the core where the hydrogen and the water were flowing sort of evenly through the same pore space. But for these measurements that we took with this channel formation during imbibition, you cannot really call that a real rel perm or rel perm measurements, because it doesn't have much meaning. But oh, sorry. Okay, so here you can see the results. So in gray, you see the results for drainage, and the green and the yellow are the results for the two different imbibition cycles. And during both of those experiments, we observed the exact same behavior of this finger formation that developed into a channel. So we observed it, we repeated the experiment, and we observed the same thing. So yeah, so this is to show that the hydrogen brine system is a very complicated system, and you get a very complex interplay of gravitational, capillary, and viscous forces, and it looks like it's behaving very differently than what we observed before. So to conclude, so the hydrogen brine rock system is water wet, which is favorable for underground hydrogen storage as it will lead to better injectivity and less trapping. Simplified systems can give important insights on the wettability characteristics and displacement behavior for underground hydrogen storage. And the current research indicates that shallower reservoirs are favorable for underground hydrogen storage because more hydrogen is trapped at higher pressures and higher drainage relative permeabilities at lower pressures, which improves the injectivity and recovery. And then visualization of hydrogen displacement at the core scale showed very different flow behavior during both drainage and imbibition as a result of the very complex interplay of viscous, capillary, and gravitational forces. So I think the way forward is to visualize these displacement processes during repeated injection and reproduction cycles because we need that understanding for underground hydrogen storage in porous reservoirs.
Excellent. Thank you very much, Maartje. It's quite a comprehensive overview of the literature on this subject, so thanks very much for this. Bart, please also introduce yourself.
Halfway.
Last one,
Bart Lomans, Shell. Thanks a lot, Maartje. Educational for my, completely not my area. Maybe therefore a stupid question. You talked a lot about wettability, but if you look in this interface, I guess it's not as black and white as it's claimed to be. So
no.
I'm wondering, what does solubility of these gases, which might differ from one to the other, impact this whole equation, let's say? So solubility of these gases in the interface.
Solubility of these gases at the interface, how that will change the wettability. Yeah, so you're right, it's not so black and white. I just presented it as black and white to try to show the meaning of wettability. So I said one, you have water wet, hydrogen wet, but of course you don't have water wet, hydrogen wet. There are many, how do you say that, in between. Yeah, you have many different, and also inside a rock you have grains that are water wet, you have grains that are hydrogen wet. So it's not that your whole rock system is one wettability. And of course, when you have, what did you say, dissolution, of course, then the wettability will change at that point, I guess. Or not the wettability, but you will, some of the, one will go over into the other, but the wettability will not change. So that system, if at that point it's water wet, then there will always stay a little bit of a water layer at that place, unless you don't have any water in your system anymore and you dry out your system.
Okay, I come back to the some online questions and then to Jan. There is a question about would rock deformation alter these quantities?
Yeah, of course. If you deform your rock, you change your pore structure, and you will change your relative permeability and your capillary pressure. So
would it be any different for hydrogen than others, or we need to study that?
I think there will be for any gas or anything you want to flow through anything. If you deform it, it will differ. It will change.
Sure. Okay. And there is another question: have the contact angles been studied against different surfaces for different, let's say, silica, clay, organic matters?
Yeah. So we with this captive bubble cell, actually Laila did most of that work. She carried out the experiments for sandstone, Berea, Bentheimer, but also for two different carbonate rocks, the Edwards and the Edwards in the Indiana. And for all these rocks, I think you got similar observations as well. But yeah, there is a difference usually in wettability between carbonate rocks and... There
are some technical questions I'll post you later about them. Maybe in discussion we can address. One last question before going to Jan is about what would be these kind of porous scale or core scale physics studies, what would be their relevance in the field scale analysis?
Well, the relative permeability and the capillary pressure curves that I just showed, those are the very important input parameters for your reservoir simulators. So these are very important, and they depend on this pore scale behavior. And I think the simplified methods that I showed, they're not necessarily, well, you can use those contact angles in pore network modeling and derive those functions, but they're more, I think, useful in getting a better understanding of the system. And I think that's important. Yeah.
My initial question, Jenne Grove from Postdoc. My initial question was about carbonates, so it's already answered. I'm a bit confused about the interfacial tension. When you compare hydrogen to methane, in one of the slides you showed that it's changing quite significantly with pressure temperature when you're going downward.
Yes, yeah.
And later on, well, it doesn't seem to be the same, or did I miss something?
No, you're right. It changes actually quite a bit with pressure and temperature. But what doesn't change is the bond number. So your interfacial tension changes, but also your density changes. And then if you use those two together, then you still end up with the same bond number. And if hydrogen, so at the same pressure and temperatures, hydrogen and methane have very similar bond numbers. And then if you have a system where you have buoyancy and capillary as your main acting forces, those two will behave the same. But it's the combination of the two and not just the interfacial tension.
Excellent point. Thanks very much, Maartje, once more for this round.